Welcome to the Space Telescope Public Lecture Series. I'm Dr. Frank Summers of the Office of Public Outreach, and it is my pleasure to be your host tonight. If you did not get one on the way in, we are giving away our wonderful lithographs, and the lithograph tonight is called A Horse of a Different Color. It's such a different color that you can't even see this color. It is infrared. This is the Horsehead Nebula seen in infrared light. And if you want to know all about what that means, turn over to the back and we've got about 300 words to talk about it. If you didn't get one on the way in, please grab one on the way out. I'm sorry. Here is the lithograph right there, all right? I always forget that I have this here. All right. If you want the PDF version of it, you don't want to actually take physical copies home, this web address down here tells you where you can get it on our Amazing Space website, okay? It's actually resource number 29, so it's one of the first ones we added to Amazing Space long ago. All right. We did the electronics nag. Tonight, Unveiling the Cosmos, Key Inventions Behind the Modern Telescope by Sarah Kendrew. And I'm really excited to have her here tonight because she's a wonderful speaker, and she will wow you tonight. Coming up on December 3rd, Serge Dietrich and Red and Brown Dwarfs, Understanding Our Smallest and Closest Substellar Neighbors. We had a talk here for our colloquium just a week or so ago that said 74% of the stars in the universe, 3/4 of the stars in the universe are red dwarfs, okay? The meek have inherited the universe, all right? This is going to go even not only red dwarfs, but do brown dwarfs, okay, all the small stuff, okay, of the universe. In January, we will not be doing January 7th because that is during the AAS meeting, the American Astronomical Society meeting. I will actually be at the AAS meeting, so we can't do it then. And we have our infamous TBA. We also have our infamous TBA repeating their talk on February 4th. Now, you may all look at this and go, okay, Frank has just been lazy this fall. He hasn't gotten any speakers. And that's only partially true, okay? We have something coming up. We have building construction coming up here in Space Telescope Science Institute, okay? They're doing a complete redesign of the lobby. They're tearing it all apart and rebuilding it all, putting it all back together. And that will affect the January, February, and March 2020 public lectures, okay? Such to a point that I wasn't sure we were going to be able to have them. I was confirmed yesterday and today that absolutely 100% we will be able to have these public lectures, okay? So I sort of was lazy in not scheduling speakers because, hey, if I didn't have to schedule them, all right, I didn't. We will, for these 3 lectures, probably be using an alternate entrance to the building, okay? So pay attention to the signs when you get here. And wheelchair access could also be affected, okay? The point is that this entrance over here and this entrance over here go directly into the lobby. That will be a construction zone, and these entrances may not be open, all right? And this is where our wheelchair ramp is, all right? So I will have more information next month, but I just wanted to put this seed in your head that building construction, January, February, March will be affected, okay? All right, but I will have speakers for you, okay? I always do, okay? Great. Let's see, our website where we will have all the information about said speakers when I get them. If you would like to watch the webcasts, you can see right here our YouTube playlist as well as our STScI webcast archive. Email, you can sign up for the lecture announcements down here. Just enter your email address and hit that subscribe, and you'll get our once a month update of what's coming up. Also on the website, we have the upcoming lectures, as well as for each lecture we have that has gone, we have both the STScI webcast as well as our YouTube of recording of the lectures. So lots and lots of ways to watch lectures. We've been doing and recording these lectures since 2005, okay? It's 14 years worth of lectures. You can binge watch. It'll take you more than a weekend to binge watch these, okay? All right. So I know that binge watching is just ever so popular these days. Email announcements to sign up the website. If you can't handle digital technology, why are you using email anyways? But you can always write it down on a piece of paper and hand it to me, and I will give it to you. If you have comments or questions, send them to publiclecture@stsci.edu. Social media, we are on Facebook, we're on Twitter, we're on YouTube, we're on Instagram. I don't think we're on Snapchat, but, or or TikTok or whatever those things are. But we have all of these channels if you would like to follow us. I myself do a tiny bit on Facebook and Twitter every now and then. After the lecture tonight, the Maryland Space Grant Observatory tells me it is clear enough out that they will be doing observing. Although we got a large audience tonight. Sarah, you drew them in. I mean, this is a big audience, okay? And they can only take a certain number of people. If you have already gone to the observatory recently, they ask that you let others who haven't gone to the observatory go. But basically, everyone who wants to go collects down here at the end of the lecture. If I forget, somebody remind me, okay? If you cannot go tonight, they have their open houses on Friday evenings. If you go to md.spacegrant.org, you'll find this web page with about their open houses, and this observatory status bar right there will be filled in by the evening on Friday and tell you whether or not they're going to be open on Friday evenings. Okay? All right, now my segment, the news from the universe for November 2019. Our first story, it came from outer space. Part 2, the sequel, the dive-bombing comet. All right, so people remember the first movie, right? All right, well, let's go back over the first movie. The first movie was about this object, 1I 2017 U1 Oumuamua. Yes, that's actually the name that they came up with. All right, and that 1I says it is the first interstellar object, okay? And this is an artist's impression of it around about the time that Hubble took an image of it way back when, and Hubble got, not great data on it, okay? Matter of fact, the data on Oumuamua all sort of looked like this. Yeah, the problem with Oumuamua was that it was not discovered until it was already leaving the solar system, okay? It came in, made a nice tight loop past the sun, and it was discovered, and we really didn't get great observations of it. This was its orbit. It actually came inside the orbit of Mercury, and it was discovered, and it was on its way out, and we really didn't get great observations of Oumuamua. We weren't able to truly characterize it much, all right? So while it was an exception, it was the first interstellar object, and that was exciting, it wasn't exciting enough for us geeks because we didn't get details of what it's really like. All we got was that it's probably very elongated and had an interesting spin cycle to it and everything, all right? And so, we knew that there could be other things coming through. So once you've got one object that you know it's possible to find interstellar objects, what are we going to do? We're going to keep our eyes open, all right? And this year, we did find another one, okay? This is C2019 Q4 Borisov. And again, you can see, yeah, it's just this tiny little dot, okay? But Borisov was discovered on its way into the solar system, okay? And at first we were like, oh, it looks like it could be an interstellar object. It was discovered in August, and they had to look through it, and they kept following in September and October, and they finally were able to conclude that, yes, it is a hyperbolic orbit. It is not from this solar system. It is not gravitationally bound to the sun, okay? And whereas Oumuamua had this orbit that came in and went back out really sharply, Borisov, I call it the dive-bombing comet because it came up and down. It's coming down through the plane of the solar system on a much more elongated orbit. So catching it as it's coming down, we're able to watch it going through. And as we studied it further and further, we saw that it's not just a dot, but it's a dot with some fuzz around it, okay? It looks like a comet, all right? So this is the first confirmed interstellar comet, all right? We could not confirm what Oumuamua was. It's more considered to be more asteroid-like than comet-like. This is confirmed to be comet-like. So what's going to happen? Every telescope that can is going to study Borisov. Who are you going to call? You're going to call Hubble. Hubble went and took a look at it to try and get a look at it. And so Hubble got a very, very clear picture of a very, very fuzzy object. This is Hubble's image of Borisov. Now it's much higher resolution, but you know, as we predicted, we're sitting in the news meeting going, yeah, it's going to be a really high resolution picture of something that's just a fuzzball, and it is. And that's what comets are, because the comet nucleus is actually hidden deep down inside the coma of the comet. The gases that escape from the comet hide the shape of the comet inside it. You actually have to fly up to it, which of course is not possible for something traveling at the kind of speed an interstellar comet is flying at. We can't catch up to this. We would have had to have started planning about 5 years ago in order to be able to catch up to something like this and see what it really looks like. However, this is still on its way inward, okay? So our coming attractions are that it reaches perihelion on December 7th, 2019. At that time, it'll be about 300 million kilometers, about 2 astronomical units from the sun, as well as about the same 2 AU from Earth, okay? So we will get a reasonably good view of this, all right, as it passes through. It will be observable through late 2020. One of the predictions I saw said through September of next year, we'll be able to follow it, all right? And we're going to look at it and try and see if we can figure out its actual size underneath all that fuzz, whether or not there's shape, because you can get the light curve of if it's rotating and such. But more importantly, what I think is most important is the composition. Are other solar systems where this comet would have formed out of the same types of materials that form in our solar system? We look at the gases, we can get the composition of that comet and compare it to the gases of comets that we see in our own solar system. That, to me, is going to be the coolest thing we're going to find out. So stay tuned. It will at least be a trilogy, if not even more, in terms of the number of sequels that we'll have about the comet Borisov. But wait till after December when we go through perihelion, we'll have some good observations. Okay? Another thing happening in our solar system that you will hear about is the transit of Mercury on November 11th, 2019, which is, next Monday, right? Okay. Do you all remember that we had a transit of Venus in 2012? Yeah, this was my favorite picture of the transit of Venus. I think this was at Metro Center. She was transferring from the orange line to the blue line and such. Now, the transit of Venus actually is about when the planet Venus passes in front of the sun. All right, and here you see this black spot right here. That is the shadow of Venus on the surface of the sun. And transits of Venus are extremely rare. You get 2 8 years apart, and then there's another 100 years or so before you get another one. All right? And we had our 2 in 2004 and 2012, and we will not have another one in our lifetimes, okay? It'll be 21 something or other before there's another transit of Venus. So you are not going to see another transit of Venus unless you're cryogenically frozen and somehow survive for another 100 years. I don't really plan on that. Transits of Mercury, however, are not so uncommon. They occur about 6 times every century, okay? And so there is the transit of Venus, and see if you can find the transit of Mercury here. Yeah, I'm sure some of you can, but just in case you can't, it's right there, all right? It looks like another sunspot, except for it's a perfectly circular small sunspot, all right? So the transit of Mercury is a lot harder to see, okay? And so it occurs on November 11th. It starts at 7:35 a.m. Eastern Standard Time, finishes around 1 p.m. Eastern Standard Time. And I have to warn you, if you try to look at it, never look directly at the sun. That's part of our astronomer's creed, that we have to say that every single time. You need to use things like solar-safe filters. Remember these eclipse glasses from the 2017 eclipse? I hope you save them for the 2024 eclipse. You can use them to look at the sun for the transit of Mercury, and you will not see it. It's just too small, okay? I tried today. I was like staring at the sun going, could I possibly see the transit of Mercury? No, it's too small. At least my old eyes would never be able to, without assistance, see the transit of Mercury. All right, so if people who are gonna see it will want to use telescopes, and if you're going to do it with a telescope, you'll want to go to a place like eclipsewise.com, where Fred Espenak, the guru of eclipses, has diagrams like this to show you where in the world it is going to be visible, and if you do look at it with a telescope, what path you can expect Mercury to take across the face. So you're not going to be able to see the transit of Mercury. But this is sort of a good excuse for me to show what you can see with a small telescope, okay? Because this was posted on Facebook by the Harford County Astronomical Society just a few weeks ago. This transit is the International Space Station transiting across the sun, okay? It takes 1.6 seconds for the International Space Station to transit across the sun, and they got the pick, okay? Richard Fentz got the pick. Not only did he get this pick, he got 50 pictures of the International Space Station transiting across the sun in that 1.6 seconds. All right, and this is a small telescope up in Harford County, okay? And this was an amazing thing. I saw it on Facebook. I immediately wrote to him and said, please let me use this in my public talks, because that's just a really cool pic of the International Space Station transiting. So transits, they're kind of cool, all right? All right, finally, one last thing. Let's talk about galaxy goulash. And some of you may think I'm misspelling here, but I am not. Because we all know about goulash, right? Hungarian goulash, okay? It's a mixture of meat and vegetables and a good hearty stew, great for these fall days like this. And so we have this goulash, but there can be considered galaxy goulash, okay? And what would we consider galaxy goulash? Well, that would be a big mixture of all these galaxies all mixed up together, sort of like what we did for Hubble's 18th anniversary, released all these images of galaxy collisions and galaxy interactions, and the galaxies are all mixed up and together. So, where do we get the name galaxy goulash, right? Well, it's when one of these galaxy collisions and has a really spooky look to it. Ooh. Where you've got the cores of the galaxy forming the eyes, and all of the tidal tails and all that bright star formation forming the head of, as the press release said, of interesting looking ghoul. Although, I gotta say, when I looked at it, it didn't really look like a ghoul to me, or spooky. It kind of resembled something from Star Trek. Star Wars. I saw C-3PO in it, okay? So I had to create this animated GIF. All right. So that was our Halloween release of these ghoulish galaxies that were together, making sort of a ghoulish head out of the galaxy configuration. All right? And that's our News from the Universe for November. Let's go on to our featured speaker. Our speaker tonight is Dr. Sarah Kendrew. She is from the European Space Agency, but she is here at the Space Telescope Science Institute. We have, how many ESA employees do we have in the building? About 15, okay? So there's we talk about collaborations between NASA and ESA, and you think if we're here and they're there, no, we got people, working together. And she works on the James Webb Space Telescope, the mid-infrared instrument called MIRI, And she's also one of the amazing people who works on the .astro conference, which is a conference that tries to reinvent how we do astronomy. So she's very forward-thinking in how she approaches astronomy, and she's been working on instrumentation her entire career. She got her PhD at University College London, and I can't remember the various postdocs she did, but she did a lot of very prestigious things. She's an amazing person. Ladies and gentlemen, Dr. Sarah Kendrew.
Thank you, Frank. That's possibly the best intro I've ever had. All right. So I was going to start with introducing myself, but Frank has done that very well. Is this working? Is this coming?
Let's see what happened. Did you click? You're on one, aren't you?
I think that's, yeah. Oh, I think it's picking it up now. Yeah, there we go. All right, good. So thank you all very much for coming tonight. I'm very pleased to be here, and I get to talk about my pet subject. So as Frank said, I work for the European Space Agency, but based here, working on one of the James Webb Space Telescope instruments. I've been here for about three and a half years, yeah. So as you know, here from the building, we are responsible for the scientific operations of the Hubble Space Telescope, which has been in space doing amazing science, gathering amazing data for the world's astronomy community for almost 30 years now. And in a few years' time, it will be joined by its successor, the James Webb Space Telescope. This is a very recent picture of James Webb in the clean room at Northrop Grumman in California. The observatory is fully assembled. You can see the mirror and the sun shield, and the instruments are also all fully assembled now. But of course, our telescopes are not all in space. We have numerous large and small telescopes all over the world. Many of them are in these beautiful remote locations on very high mountaintops. We have telescopes that every night now shoot lasers into the sky, which is just amazing. So I've worked my whole career on basically developing instruments and technology for telescopes, both on the ground and in space. And for me, the role of technology in astronomy and how it drives astronomy is like a really fascinating subject. So with the aid of all these telescopes, we have been able to build up an amazing picture of the entire universe. So we know the universe came into being in this big cataclysmic event that we call the Big Bang around 13.7 billion years ago. And you know, after this period of rapid expansion that we call inflation, the kind of hot soup of the universe cooled into atoms, forming the first stars and galaxies that illuminated and ionized the universe. Today, we know that the universe is expanding all around us. And even more, we actually know this expansion is accelerating under the influence of this very bizarre force that we call dark energy, that we have absolutely no idea what it actually is. So we've got this huge picture, but lots of open questions as well. One of my favorite amazing discoveries is the discovery that we have a supermassive black hole at the heart of our Milky Way galaxy. And the way we know that is that we've been able to trace the motions of stars right at the heart of the galaxy, basically whizzing around this central point, which is basically the heart of the galaxy, the center of the galaxy. And by tracking these stars over about more than 20 years now, we're able to basically measure the mass of this central object and deduce that this is a supermassive black hole weighing as much as about 4 million suns. We have discovered an amazing wealth of planetary systems outside of our own. So this, you know, the first ever exoplanet around a normal sun-like star was only discovered just in 1995. so fairly recently, but this is a field that has absolutely exploded. And we now know that our solar system isn't unique and that planetary systems are probably just natural byproducts of the formation of stars. And so you just see here, this is an actual representation of known exoplanet systems in our solar neighborhood. So you can see we are very much not alone. So those are some of the, that's kind of like some of the really exciting things that we've learned in our time in modern astronomy. But, astronomy is actually like one of the most ancient natural sciences, probably the most ancient natural science. So there's evidence going back thousands of years, if not even tens of thousands of years, that early humans and civilizations were actively watching the night sky and watching celestial objects and tracking their motions. And it's very normal because they were basically, this was the way that they kept time. It was the first kind of timekeeping system. And it would tell those humans, about changes in the seasons and in the weather, which would kind of herald, changes in the availability of food. So really this, had a kind of really outsized influence on their day-to-day life. So this is, stargazing is, as old as humanity itself, really. And because of this huge influence of the night sky and celestial objects on people's day-to-day lives, it also means it was very closely tied into their belief systems and gods and worship. And this is actually something I've always really liked astronomy, and that it really kind of ties together science and discovery with traditions and culture in that way. So in that context, telescopes are an incredibly recent invention in astronomy. Telescopes were not even the first ever instruments that people started using for looking at the stars or at the night sky. So there's a whole range of early instruments, from sextants to astrolabes to I can't remember, totally blanking on the name of the thing at the end. Planisphere. These beautiful astronomical clocks. All of these particular instruments predate the invention of the first telescope. And so these were used to predict the locations of stars in the sky, or to measure the positions of stars in the sky, or certain angular distances. And it's actually really, whenever I read about this, it's really fascinating how much knowledge we had actually already gathered before the first telescopes were even, invented. We had catalogues of stars, huge catalogues of stars and their positions already charted. Things like, the planets, motions of the planets had been traced in huge amounts of detail. The actual laws of planetary motion were derived from naked eye observations. And so there was actually a huge amount of knowledge already gathered before the telescope even arrived. So that's kind of setting the scene for what I want to talk about here. Telescopes have really kind of supercharged discovery in astronomy, but we shouldn't forget everything that came before either. So astronomy as kind of an experimental science is very unique in that we can't perform experiments on our subjects in the same way that other sciences do. So we can't grow things in a petri dish, or we can't put galaxies in MRI scanners or anything like that. We have to just make do with what we see. We have just one laboratory, but our laboratory is the size of the entire universe. So our job really is to kind of just gather as much information as we possibly can, with as many different methods as we can, and then to try to kind of build up this story, of this picture of the past and the present and the future, to try and like piece everything together. In the simplest form, observational astronomy is, catching photons from space. So photons are the carrier particles for electromagnetic radiation. Photons can come in a huge range of different energies, and these different energies we call by different names, from the lowest energy, which we call radio waves, through to microwaves, infrared, visible light, to the very highest energies, which are X-rays and gamma rays. And so we want all of these photons in astronomy, basically, because all these different energies in the radiation kind of tell a different part of the story. And we have observatories to detect all these different types of radiation. And each of them use, I could give this talk for each of these different parts of the electromagnetic spectrum, because each of these, uses very different technologies and have their own history that is really interesting. But so for this talk, I am going to focus on the kind of visible and near-infrared range. Just visible light astronomy. Just a caveat for my catching photons from space, this is not fully true. So we also have telescopes that detect high-energy cosmic rays coming from astrophysical sources. And since very recently, which is very exciting, we can also detect gravitational waves from astrophysical sources. And this is like a whole new area of science. These were only first detected a few years ago. So that's very exciting, but we'll not be talking about that today very much. The basic principle of a telescope, a visible light telescope, it's just a big bucket for light, for collecting light. The telescope itself just collects the light and then brings it to a focus in a convenient location. So that can be to an eyepiece, or it can be to a camera, or another different kind of instrument. The bigger the telescope, the bigger the bucket is, the more light it can collect. So a larger telescope can, in principle, detect fainter sources because it can collect more photons. And a larger telescope can also achieve a higher resolution. And what that means is that, you can see here the little diagram, is that you can see finer detail with them. So that is basically a reason why, as soon as we understood these principles, we just wanted to keep building bigger telescopes. And that is really what's driven a lot of technological development. So the first aspect of technology I want to talk about is how to build large mirrors. So you see here a nice graphic of Galileo performing his first astronomical observations. That was in 1609, so that's the date often quoted as the invention of the telescope. The invention of the telescope is actually like a really fascinating story. There's all these theories about who knew what and when, and who told what to whom. And if you really kind of dig into the history of it, it's actually really fun. But we'll stick with 1609 here. So this first telescope that Galileo built immediately was used for some really cool discoveries, like the four big moons of Jupiter. So it was immediately put to very good use. And so this telescope was made with lenses. But very quickly after these first models, telescopes started also getting built with mirrors. Mirrors have some distinct advantages. They're a little easier to manufacture, and they're not quite as cumbersome as lenses. But both refractors using lenses and reflectors using mirrors were kind of used in parallel for quite a long time. The astronomer who really perfected the art of making large mirrors was William Herschel, who was a German astronomer working in the south of England. And he was very good at making telescope mirrors, and he had a number of telescopes in his own private observatory, which he and his sister Caroline used to watch the skies night after night. And they made some absolutely amazing discoveries. They were both incredibly accomplished. But this was the culmination of Herschel's kind of telescope building career. This was Herschel's grand 40-foot telescope. So the 40 foot refers to the length of the tube. The size of the mirror was about 48 inches in diameter. This was kind of a tourist attraction. It was actually marked on the map, so people would travel far and wide to come see this telescope. The only problem is that it just wasn't very good. And it's quite funny because Herschel would go to give all these presentations about his observations, but he would kind of gloss over the fact that they were done with the other telescopes, not with this one, because he didn't really want to admit this. But he really hit on the difficulty of building very large mirrors and very large telescopes. You can see this is an amazingly complex contraption. It was incredibly heavy. It was completely impractical to actually move around the sky. And so often he could only observe things for a very short period of time as they drifted out of the field, because it was far too difficult to actually move the telescope around. Also, the mirror, as you make a mirror bigger, it becomes a lot heavier and it becomes a lot bulkier as well. And so this is where you start getting problems. So if you want to make a mirror twice as big, you also, for it to keep its shape and not sort of sag or flop under gravity, you have to make it 4 times as thick. So you can see, as you scale up in size, you're going to end up with these huge, bulks of material. And as your bulk of your primary mirror gets bigger and bigger, the whole support structure also has to become a lot, stiffer and stronger to actually support that weight. And the whole thing is just going to very quickly become very cumbersome to use. What's more as well, so as you go, and this is still an issue today with mirrors, as you go from day to night, there's usually a very strong drop in temperature. And so a telescope mirror has to kind of thermalize. Its temperature has to adjust to the ambient temperature. And that can take a while. That settling can take a while. And if you have a mirror that's this huge bulk of material, that basically can take a very long time. And so Herschel would constantly get condensation on his mirror, which would then freeze. So he'd have like a layer of frost on it, and it wasn't very good. So Herschel, in his telescope building adventures, basically came up against this big problem where the primary mirror is kind of the heart of the telescope, and it really drives the cost of a telescope. And it's a very big engineering challenge how to increase the size of a telescope without running into these issues. And this continued to be an issue until well into the 19th, early 20th century. So a couple of solutions were found for this. So the first was pioneered here in the 1940s with the 5-meter Hale telescope at Mount Palomar Observatory, which is still in operation today. And it's actually like an amazing achievement for its time. So this 5-meter mirror was a huge step up in size from the previous kind of largest telescope. But it was clear that if they had to increase the thickness of the mirror and to scale with the diameter, that this would be completely impossible. I think even in the manufacturing process, when the glass would come out of the oven, they have to control the cooling, because otherwise the mirror can crack if it cools too quickly. And I think it was going to have to cool for something like, I don't know, it was like many, many years, decades, basically. So this was, not going to work. So they developed this technique whereby the glass, the molten glass, was kind of poured over over a mold that had this kind of removable backing structure, so that they could actually remove a huge portion of the material, but keeping these stiff ribs to that kind of maintain the stiffness and the support of the mirror surface. And so by doing this, they were able to cut down the weight of the mirror by, I think, to about 65% of the mass that if it had been, a solid block. And so this made, this was kind of key to making this telescope a success. And like I said, this telescope is still in operation today. So this is it was an amazing piece of engineering. A little bit later, in the 1980s, a technique was developed in Europe, which we call kind of active support, active optics. So in this technology, rather than trying any sort of clever manufacturing techniques like this, the idea was to not even try to have the mirror hold its own shape, just create a very thin mirror, but fix actuators on the back that can be electrically controlled, that can basically, as the mirror moves around on the sky and sags under gravity, can just nudge it back into shape. And so this was first demonstrated in the late 1980s on the 3.6 meter New Technology telescope. This is a telescope operated by the European Southern Observatory, which is a large European consortium. operating astronomical telescopes in Chile. So this telescope is still in operation today as well. And this technique is used on many large telescopes today. So it's really ingenious in that you can kind of, constantly monitor the shape of the mirror and kind of just nudge it back into shape as needed. The next step in this was to actually, and this is a technique pioneered on the 10-meter Keck telescopes in the early 90s, is to not even try to build the mirror as a single piece, but to actually build up the mirror out of tiles of smaller mirrors. So here you actually see an example. This is actually the Southern African Large Telescope in South Africa, which uses this same technology. So you can see this is just kind of like lots of different hexagonal tiles of mirrors. And this is a kind of a drawing of what the back of one of these segments looks like. So it has these support structures on the back so that every single segment can be adjusted in tip and tilt and to keep them aligned with their neighbors so that you can maintain a beautiful shape for the mirror. And as you may know, the James Webb Space Telescope marks the first time that we will launch one of these segmented mirrors into space. And indeed, we wouldn't be able to launch such a large mirror into space without segmenting it, because it's that technology that lets us fold it up so that it fits into the launch vehicle and to then kind of be deployed and kind of folded back into its full shape after launch. So this is a really amazing technology. Towards the future, this segmentation is really kind of the path to a huge scaling up in size of telescopes. So here you see a beautiful artist's impression of a next generation European ground-based telescope called the European Extremely Large Telescope. We do not waste any money on coming up with good names for our telescopes. And so the diameter of this mirror is 39 meters. You can see here, these are like, these tiny specks down here are big trucks. So you can see the size of this. This mirror will have around 800 individual segments that will all have to be tiled and its shape maintained throughout observations. So the scenery here, this telescope is under construction in the Atacama Desert in northern Chile. So it does actually look like Mars there. The second kind of technology I wanted to talk about was the ability to capture images, which led to the birth of astrophysics and also the birth of kind of surveys in astronomy. So I put here a picture of Frederick Douglass. Photography was not invented for astronomy, of course. But astronomers were very quick to cotton on. So the first kind of photographic technologies were developed in the kind of 1820s, 1830s. And these are some of the very first pictures that astronomers took with this new, with these new techniques. There were lots of really exciting firsts. So in 1840, here, an astronomer called Draper took this picture of the moon. The first picture of a solar eclipse by Bukowski, this was taken in a European observatory. This is from 1851. And so this showed us for the very first time these, the solar picture of the solar corona and these, little prominences on the limb. And really importantly as well, the first recorded spectra of stars. So here, these are spectra, so it's starlight dispersed. Astronomers knew before, before photography came along, had been able to see these spectra, but a lot of these features are kind of very faint and, were very difficult to study without actually being able to record them properly. So with the advent of photography, these could for the first time kind of really be kind of compared and studied, and this really kind of gave rise to astrophysics as a science, where people could really study like what the physics of what was happening inside stars. It was kind of quite a big, this is a really interesting period in the history of science. This was kind of, there was a lot of enthusiasm about invention and innovation in Europe as well as in North America around this time. And the fact also that now these images could be reproduced and printed meant that they were, it was like the first time that sort of astronomical images would appear in the media, in newspapers. And it generated a huge amount of enthusiasm for astronomy in society in general. From a scientific point of view, it was also, there was this real feeling that it was the first time they could really have objective recordings of what was happening in the sky. Previously, it would always relied on notes and sketches that were taken by astronomers, which are obviously a lot more kind of individual and subjective. For me, this is a really amazing image. So this is was taken a photograph taken of the Orion Nebula by someone called Andrew Ainsley Common in 1883. And this was one of the first photographs that showed very faint stars that couldn't be seen with the naked eye. So it was kind of the first time that you could sort of expose for longer, and then when the photographs were processed, it would reveal kind of new stars in there that people hadn't been able to see before. So this was kind of really, must have been a really amazing experience. You see for the first time these things which have been hidden from the eye from before. And I think astronomers were very quick to realize the potential and the kind of paradigm shift that this technology was bringing. So here's a quote from Charles Pritchard, who was a civilian professor of astronomy at Oxford in the late 1880s. It's a little bit long-winded, but basically he says, this is, with photography, we can actually now always compare back to, we have like points of comparison, like to be able to see if things have changed, because we have that absolute recording of what something looked like at a particular time. So we don't always have to like draw sketches and things like that. It's like very easy to now compare. And this is still kind of what we do, when we look for things that change in the sky, we just compare different images. Photography also kind of paved the way for doing astronomy by surveys. So rather than surveys is when rather than look at a particular object, you just kind of map the sky, huge parts of the sky in one go. And then you can use those photographs, to kind of pore over them and study what's there and catalog all the objects that are visible. This is something, this is a very interesting kind of sociological period in astronomy as well, because this work of poring over these giant images with, that contained, thousands of stars or lots and lots of stellar spectra was considered kind of dull and rote work and something that even women could do. And also, you didn't have to pay women as much as men to do it. And so around this era, kind of there's this entire generation of incredibly smart women who did this work and who made these incredible discoveries, basically based on their work with these large-scale surveys. So here's just a picture of two of the the best-known names from that period. You have Annie Jump Cannon, who just classified, who looked at 350,000 stellar spectra by eye and of stars, and basically came up with a classification scheme based on the chemistry, and that is still the classification scheme we use today. So that's a really transformative work that she did. Henrietta Swan Leavitt, similarly, they both worked at Harvard College Observatory. Just from looking at lots and lots of images of stars, derived a relationship between the period and the luminosity of a particular type of variable star, which we call the Cepheid variables, which was later used by Hubble to derive distances to galaxies, and which allowed him to discover the expansion of the universe. And again, this is a relationship we still use today. We still use these Cepheid variable stars to measure distances to things. So this is kind of like an amazing kind of period. This photography and these wide field photographic surveys were a really amazing period in astronomy. Photography kind of was the lay of the land in imaging well into the 20th century. The most famous of the photographic surveys is probably the Palomar Optical Sky Survey. There was a series of these. This is an image from POS 1, from the first one, which was executed over a period of a decade. So it was very long, over a very long period of time, and created an absolutely amazing data set that led to the discovery of clusters of galaxies, thousands of new star clusters in the Milky Way galaxy, and lots of new other interesting objects like planetary nebulae. But photographic plates had their problems. There were not, there were a lot of problems with using them. So there were these large glass plates, and so, particularly when you're doing these huge, large-scale surveys, you were generating a lot of plates, and so they were kind of cumbersome to store. You couldn't reuse them, so you always had to get new ones. Also, the efficiency with which so photography is kind of a chemical process, so you have a kind of a photosensitive emulsion that goes on this glass plate and then reacts to the incoming light. But the efficiency with which that conversion happens is not very high, and could be quite different between different parts of the plate or between different plates. And the response was also not very linear, so it was quite hard to use the brightness you measure in a photograph to really accurately measure the actual intrinsic brightness of the star. So these were kind of, niggly problems that did, for really being able to do precision science, kind of called for a different solution. That came in the form of electronic imaging using CCDs, or charge-coupled devices. What these devices do, or the basis of this type of imaging, is to harness what's called the photoelectric effect, which is actually, Einstein came up with the theory for what happens in the photoelectric effect in the early 1900s. So before that, it had been known for quite some time that if you irradiate certain materials, their electrical properties would change, which is kind of weird. The theory behind the photoelectric effect that Einstein, very cleverly kind of derived, is that the energy of the incoming light, so when radiation hits a material, releases electrons in the kind of substrate of the material. At the time when Einstein came up with the theory, we didn't know yet what photons were, so he framed it slightly differently. But basically, what happens is that you have photons coming in carrying energy, and they interact with the with the material, releasing electrons. And as it turns out, for a given material, this is a very predictable response, and it's immediate, and it's repeatable as well. So this basically gives a really clever way of using an electrical current to learn about the properties of the radiation that's hitting the material. So that was, the photoelectric effect was kind of in the early 20th century. The real breakthrough for imaging came when these two gentlemen here, Smith and Boyle, here it's shown at their Nobel Prize ceremony. They worked at AT&T Bell Labs when they figured out a way of sort of transferring a charge sort of between, this is kind of a little sort of bucket analogy. They figured out a way of, if you had every little element has sort of photosensitive element, little bit on here, and then you would collect the charge, and they figured out how to then transfer the charge along kind of rows so that you could then kind of get the signal from the material and reconstruct a two-dimensional image. Sorry, I hope that was clear. So basically that you have, this whole array, this is what a CCD looks like, a charge-coupled device. It's got all these little squares, which we call pixels. And at every one of these pixels, if you have incident radiation, it will generate that particular charge. And then using this charge coupling mechanism, you can actually read that out and reconstruct what the image looked like. So being able to use this technology and use this effect and harness it to produce a two-dimensional image, that was really kind of the key breakthrough for these charge-coupled devices. The great thing about it is that, again, it's a very linear response over a very long range of energies, and it's very predictable. So you can basically calibrate it very well. And they have quite high quantum efficiency, so a very high fraction of incident photons will generate that current. And what's also great is that you can actually just mosaic them. So one of these little CCD devices is quite small and can cover only a small portion of the sky. But if you can tile them together, you can actually get like very wide field cameras. And so from around, so these devices were invented sort of in the, I think in the late 1960s. But it took quite a while. There was a lot of early development that needed to happen for these to become really useful for astronomy. But from sort of around the 1980s, CCDs have really been sort of the key technology for imaging at visible wavelengths.
How big is that CCD?
I knew as soon as I said it, I thought, actually, I don't know how big this is. But they can be a few centimeters, yeah, like something like that. What's been great as well is that so a lot of these technologies kind of like impact each other as well. So CCDs have been really critical for other types of technological advances. For manufacturing mirrors, for example, by being able to do electronic imaging, we were able to develop new measurement techniques for optics, so to be able to actually measure the shapes of mirrors better in the lab while we're manufacturing them for telescopes. So we would not be able to build these types of mirrors to that level of accuracy without CCD technology. Similarly, space astronomy would never have been able to flourish to the extent that it has without the ability to record and digitize, record images electronically and then digitize them so that they could be transmitted back to Earth. And the final technology that I'm going to talk about for adaptive optics also relies very heavily on having CCD technology in there. So in the future, to kind of highlight what's happening with this in the future, I put an image here of this future telescope called the LSST, the Large Synoptic Survey Telescope, which is basically the biggest digital camera that's ever built. You can see here what the CCD focal plane looks like for this camera. So you see here the full moon. This is the actual size of the full moon, just for scale. This whole mosaic of CCDs has 3.2 billion pixels. It covers 3.5 square degrees field of view. So again, compare that to the size of the full moon. And it's a mosaic of 189 individual CCD sensors. And this whole camera that this is kind of at the heart of is like the size of a small car. It weighs over 6,000 pounds. So this telescope is going to absolutely blow every other survey out of the water when it comes into operation in a few years' time. It's currently under construction in Chile, and it's going to be able to map the sky with that field of view at a huge speed, so that it's going to be able to repeat measurements very quickly and measure and find things that change. I think the estimate is that it will discover several million supernovae every night. Okay. Yeah. Okay. Telescopes in space. I'm not going to talk about this for too long, but I couldn't really give this talk here without talking about telescopes going into space. This has obviously been one of the biggest transformations in modern astronomy. So why do we want our telescopes to go to space? Well, the Earth's atmosphere is great for us. Life would, as we know it, would not be sustainable on Earth without the atmosphere protecting us from harmful radiation, kind of maintaining a thermal balance, kind of balancing out the energy that we get from the sun. But it's terrible for astronomy, and this is, I think, that the thing that unifies modern astronomers to those from 10,000 years ago is that we just complain about the weather all the time, about the clouds. This is a very kind of crude little sketch of what happens when starlight comes through the atmosphere. The atmosphere is basically this layer of thick, churning gas. Starlight is traveling through space and basically doesn't really encounter many obstacles. But then when it hits the atmosphere, which is this kind of like this gassy mess that's constantly turning, constantly changing, the light kind of gets distorted, and then it creates this kind of, instead of a nice image, it creates this fuzzy blob. And this is actually a recording of what the image of a star looks like, as on a CCD chip, as you see it through the atmosphere. So instead of like a nice point source, like a nice point-like image, you see this fuzzy mess here of all these like different speckles that are constantly moving around and changing in brightness. So that's kind of what happens when you observe, when you take an image of a star through the atmosphere. As you expose this over time, it would just kind of build up and it would just be this big blurry mess. So even the best telescopes don't ever get to achieve what they're theoretically capable of, because the quality of the images is limited by what the atmosphere does to them. What's more is that some light doesn't even get through the atmosphere, so there's huge parts of this electromagnetic spectrum that is actually absorbed, where the radiation is absorbed by molecules in the atmosphere. I've just been talking here about this visible near-infrared portion of the spectrum, but you see here in the infrared, this is 100% means the light is completely blocked. 0 is everything gets through. So you see here in the infrared, if we want to observe at infrared wavelengths from the ground, we have to do it in these windows where the atmosphere is actually letting it through. If we want to be able to observe really continuously over this whole kind of range, we have to go into space. So the history of space astronomy and the space program in general is obviously a huge subject and has an incredibly rich history that I wasn't really able to do justice. But just, the Hubble Space Telescope is the first kind of major observatory that was launched into space and has had, a huge transformative impact on astronomy, but also kind of beyond, I think. So I just wanted to highlight two people who were like really seminal in the Hubble Space Telescope coming to being, and and as a consequence, also like all other space telescopes, we have a huge range of space telescopes in operation today. The first was Lyman Spitzer, who was actually the first person to really formally report on the potential of a large space-based observatory really far back already. And this is eventually what became the Hubble Space Telescope. The second person I kind of wanted to highlight was Nancy Roman, who worked for NASA and who played a really critical role in kind of rallying the astronomical community and organizing the astronomical community to maximum impact to really kind of be able to advocate for this project and to kind of make it into reality. And so, yeah, the impact of Hubble and of its fellow space telescopes has been completely, transformative, as I said. This image alone, which is the Hubble Ultra Deep Field, kind of has, completely changed astronomy in that it showed. So this is the Ultra Deep Field, which is not the very first generation of this image, but the very first Hubble Deep Field showed so many more galaxies than anyone had expected, really, and in so many more different shapes and sizes and colors that it kind of created almost instantly created a whole new field of galaxy evolution studies and high redshift astronomy, really being able to study the early universe. And that was really the Hubble being above the Earth's atmosphere, not, being able to produce these incredibly sharp images, even though it's not a huge telescope, and having this incredibly kind of stable observing environment is really what enabled this type of science. But again, it's just, also good to highlight that space astronomy relied on several of the other technologies that I'm talking about, like advances in electronic imaging and being able to manufacture good quality and lightweight mirrors as well. Again, in space astronomy, this is incredibly condensed down, obviously, like the overview of space astronomy, but just here are just some cool missions. As you know, we have the James Webb Space Telescope launching in a couple of years' time, and hopefully a few years after that, the WFIRST mission as well, which people here in the building are working very hard on. And as I work for ESA, I wanted to also highlight our next ESA launch, which is a mission called CHAOPS, which is going to study exoplanets, which is actually launching later this year. The final piece of technology I wanted to talk about was what we've developed to overcome the atmosphere. So I just mentioned before that the Earth's atmosphere is this barrier that we just can't, that introduces a lot of problems into astronomical images that we can't circumvent. Well, actually, we can. So this is, again, a kind of a very, quite a recent technology. This is actually what I did my PhD in, so I have a very big soft spot for what I'm showing in the next few slides. Just repeated this one here, just to remind you, Earth's atmosphere, terrible for astronomy. So that's what we're dealing with. So in the 1990s, well, actually, going way back before that already, this is a technology that was developed in the military, basically here in the United States. So there was in the 70s, I think mostly 70s, 80s, there was huge interest in being able to take images of Soviet satellites from the ground to be able to see, what they were doing and everything. And but you're trying to do the same thing, just in the other direction. They were trying to take images of satellites up there. But again, they were trying to take images through the atmosphere, which would be very distorted and couldn't see the level of detail that they wanted to see. So this whole kind of array of technologies was developed, which we collectively call adaptive optics, which is where you correct for the effects of this atmospheric turbulence in real time during an observation. So there are 3 steps to this process. Whoops, hit the wrong button. There is a sensing step. So, nope, here. The light comes in, bounces off a mirror, and then at this point, this is the scientist, but you split, the part of the light is split off towards a measurement device, which we call a wavefront sensor. And at this measurement step, the effects of the atmospheric turbulence are characterized, and then a correction, there's basically a computation that then calculates how to correct for that turbulence at that moment. And then the commands are sent to this optic here, which is basically a bendy mirror. So these small mirrors, about the size of, in original systems, about this size, and have actuators mounted on the back of them that can respond very, very quickly. And so this mirror can be shaped in the shape that's required exactly to cancel out the distortions of the light that's coming in, to kind of push it back into the right shape. Now, the big challenge is, so this then forms this sort of closed-loop system where you're constantly measuring, constantly correcting, and sort of to try and basically keep the image nice and sharp and still. Now, the problem is that the turbulence in the atmosphere changes on timescales of milliseconds. So this whole loop has to be performed in like hundreds of times, if not 1,000 times per second. So you can see how this could be, incredibly challenging. But a lot of the basic kind of technological developments were done in the military here in the US. And these results, but in parallel, there was also a lot of research going on in Europe. And then I think in the late 1980s, it became clear that, well, the need for this in the military had kind of, because the Cold War was kind of coming to an end, and this was not such a high priority. But then there was a big push to basically declassify all these results so that the astronomical community could benefit, because the benefits to astronomy were very clear from the start. And also, there were scientists in France who were kind of doing research, very similar research in the same area, so they kind of realized, like, we should really just be collaborating on this. And so this technology has been implemented on large telescopes since the 90s, yeah. Here you can actually see, so while I've been talking here, you can actually see here the effect of switching on the adaptive optics system. So this is an image of a very dense star field towards the center of our galaxy in the near infrared. And you can see, without adaptive optics, these stars are all very blurry. And when you switch the system on, it takes a while for the system to really, to start working. But then you can see the improvement in the image quality is just amazing. And you can pick out lots and lots more detail, lots of small little faint stars that were previously just sort of blurred out. So this has been for ground-based astronomy, has really kind of blown new life into ground-based telescopes, because suddenly this really fundamental thing that was causing problems can actually now be fixed. And so this has been a huge area of research. Really cool aspect of adaptive optics is if you don't want to lose the light, if you use your actual science target to perform the measurement that's needed to make the correction, you're kind of losing some of your light because you're having to channel it to a different system. So the way to avoid having to do that is to create an artificial star in the sky. So if, say, for example, you're observing something here, you can actually kind of using a very powerful laser, you can actually create artificial stars. So these are very powerful lasers that shoot up high into the atmosphere, and at about 90 kilometers of altitude, they cause sodium atoms to kind of jiggle. They excite sodium atoms high up in the atmosphere, which emits light. So they basically create a little artificial star, and you can, with these lasers, you can put the artificial star wherever you need it, close to where you're observing. And so now, again, this is something that's very commonly used, and it allows the correction from the adaptive optics systems to be better, or to perform it over a larger field of view. And so this is, an artist's impression, but this is actually these are real pictures. We even now are able to use these constellations of these laser guide stars to cover a wider field of view. This is these are some first images of a system that came into operation a couple of years ago, three years ago maybe, on a telescope in South America. It shows an object called BNKL, which is an explosive outflow from a very young massive star that's forming in the Orion star-forming complex. So these are kind of Hubble quality images, but these were taken from the ground with one of these advanced new adaptive optics systems that provide this constant correction for the effects of turbulence. So you can see, and this is over a fairly large field of view as well, so you can see like the real amazing detail in all these explosion fingers that are kind of shooting out from this central object. So that's like, when I was doing my PhD research, this was all very much still in its infancy. So for me, these are kind of incredible to see. So to summarize, this adaptive optics technology has kind of really breathed new life into ground-based technologies, into ground-based telescopes, and it's kind of paved the way for the next generation of big ground-based telescopes in the future. which can now kind of really reach their full potential by being able to apply these corrections. It's a very multidisciplinary technology. It's a combination of optics, electronics, very fast signal processing, and powerful laser technology. And really interesting as well is this is something that's found application in industry and medicine. So this type of technology, adaptive optics, is used for very high resolution imaging of the retina, for example. And a number of other, like in microscopy, certain types of microscopy it's used as well to increase the resolution of images. Okay, so kind of going to just summarize there. Very high level summary. Just for me, technology and innovation are like really key to scientific progress, and this is one of my pet subjects. Is that I find it really fascinating how they kind of interplay. And we have some amazing new giant telescopes coming in the future, both in space and on the ground, that are really going to help us, with the aid of all this advanced technology, are going to help us answer these really fundamental questions about nature of dark energy and the formation and evolution of galaxies, and of life in the universe. So thank you very much.
All right, do we have questions for our speaker? Let's start way back in the corner up there, just to make Grant run.
Hello, can I ask 2 questions?
Yep.
First question has to do with the intersection of quantum physics on the CCD telescope. If the suggestions from the double-slit experiment are correct, that these particles can exist in 2 places at the same time, then how can the pixels be sure that they're accurately measuring particles? They're not counting a particle that has already been counted by another pixel. And second question is, I assume the adaptive optics do not exist in the mass-produced, commercially available telescopes. Am I correct on that?
Actually, I'm going to answer that one first because that's easier.
Okay.
Yeah, that is actually a really big growth area now. I think there are now beginning to be some commercial off-the-shelf systems that provide some simple adaptive optics correction. Not like super advanced, but, and I think you probably need like a pretty, I don't think these are, maybe not like fully like plug and play, but I have heard that they are now available to provide some correction to improve the images. Your first question about CCDs. I think you've hit on something. I'm not sure it's really. I mean, yeah, it really gets into the kind of material science of semiconductors. I mean, yes, there is always like an uncertainty, and there are some like weird effects sometimes in these these materials that we use for CCDs. So there is always like some uncertainty, but. Yeah, I'm not sure I'm answering. I don't know. Does that answer your question a little bit?
There's just a margin of error that you have to.
Yeah, there are like statistical effects in there, and there is there is sort of quantum nature of matter basically that does there's the probability aspect is in there in the response of the CCD. Yes.
Thank you.
All right, other questions down here. Where are we, Grant? Grant is saying that the microphone is not working. So to ask your question, we'll repeat it.
Does adaptive optics have any application in space telescopes?
So I'll repeat it. Does adaptive optics have any application for space telescopes?
Well, the real key thing with the adaptive optics is a very fast correction. And this is, that's like in that form is not really needed in space, but there are, because my PhD was actually sort of a crossover between ground and space, and so there is definitely application for having that ability to live correct images in space. That's particularly to sort of compensate for like thermal effects. It also it reduces. Your mirror doesn't have to be fully perfect if you know you can actually like nudge it into shape while you're observing. So in that sense, it like reduces the risk a bit on the optics in space. So there is some application for it, but it's in a kind of slightly different form, basically.
All right, down front here.
And this time, hold on.
We have the
Speaker now. How about that? Question on the James Webb. How many optical experiments are on board? How many? Yes.
There are four science instruments, four individual science instruments, which each of these like has a whole range of things they can do. So the instrument I work on, for example, MIRI, it has a camera on board. It has 2 different spectrometers on board, and it can also do what's called chronographic imaging. So you do imaging with the central object blocked out, so you can see faint things around it. So there are 4 individual instruments, but each of these has a number of like different functionalities. So that they're, you know, for people who want to propose to use it, they have access to a huge range of different capabilities.
Thank you.
over on the left there.
So I realize it's a lot of it's money driven. How big could we conceivably get?
That's a really good question. Something that
On the ground or in space?
Either or.
Yeah,
I mean,
exactly.
seriously, dark side of the moon would be awesome.
Yeah, it really depends very much who you talk to. The 39-meter ground-based telescope I showed you the nice artist conception of, that was back in the day when I started my PhD. That was actually a 100-meter telescope, but there was already then a lot of debate about whether this was technically feasible, whether we should build it. Again, the same questions come up with space as well. I mean, already now we're planning the next generation of large space observatories. There are just some things that you really just need a bigger telescope for. That a clever idea isn't going to help you. You really need the size. But yeah, I don't know. It's very interesting. Like you say, this is all very, very money driven. It's also what kind of technical risk you're willing to accept and things like that.
All right, so I mean, you said 39 meters for the ground. I think the largest space one I've seen proposed is 16 meters.
I'm not
Yeah,
sure.
for the Louvre
Is
mission.
Louvre 16?
Well, they want it to be 16.
Yeah.
They would love it to be 16, let's say that. All right, go ahead.
I think about 20 years ago, maybe not quite that long ago, I saw a photograph. I think it was using speckle interferometry that showed the disk of Betelgeuse with sunspots.
Yep.
Is anybody still doing that?
Yes, that technique does get used, and actually, based on that technique, there's actually a lot more, a lot of new types of how to describe, but yeah, techniques, observational techniques that use the same principle as like speckle interferometry to really get like incredibly high resolution images. I actually worked on one instrument which has recently produced a whole lot of results, which combines the light from different telescopes and interferometry in the near infrared to be able to measure extremely high precision positions of objects. And so with that, we've been able to measure, like take direct spectra of exoplanets and things like that as well. So yes, that's definitely still alive.
Thank you.
Yeah, I will comment that we here at Hubble constantly see lots of people trying to say, oh, we've got just as good resolution as Hubble, whether it's using adaptive optics or through speckle. Speckle is very fast observations. And they are correct that for very short very small field of view type things, they can get Hubble exposure, but they can't get Hubble exposure over wide field of view. You could never do like the Orion Nebula image that we have. You couldn't do that whole Orion Nebula via adaptive optics or via speckle or anything like that. But we're hoping that in the future we can start to do that from the ground. You know, astronomers will push that technology forward, but every technology will have its limitations.
Yeah, that's a very good point, the actual comparison of the fields. So a lot of these high resolution techniques from the ground are limited to very small fields of view.
Other questions? I thought I saw.
I've been listening to all this about how heavy these mirrors are. Have they gone back to the basic mirror using mercury vapor, mercury liquid?
There are concepts for that, yes. There are some groups who...
Where you're from, they have labs underground, which are supposed to be secret, but they're supposed to be 10 years ahead of us, too. So you haven't got gist of this, or...
Well, actually, the main liquid mirror place, I think, that works on these concepts for liquid mirror telescopes, which is sort of, you know, kind of rotating. I think it's rotating Mercury.
It is. It's rotating. Right? Yes, in Canada,
yeah.
University of Laval.
Yeah, they work on this. Yeah.
I'm glad that's happening. Thank you.
And what's really cool is the amount of mercury they need to use, because they can set the substrate to almost the shape they need. It's just a tiny bit of mercury that they need, but unfortunately, it's also going to be just a telescope pointing straight up. Because if you're rotating it, you know, it has to have an axis. So it's a panning telescope. Other questions?
I have two simple questions, kind of intriguing. One is, I worked a lot with space telescopes imaging the Earth, and we don't have an atmospheric problem there. In fact, the loss of resolution decreases with altitude. Now, why do we have the problem when we look the other way? That's my first question. Well, I think it's an intriguing question, and I do know the answer to that, I should say. The other question is, on a segmented mirror, how close does a segmented mirror come to matching the resolution of the continuous surface, say at a half micron wavelength?
The resolution is one side of it. I think the thing where it differs from what the continuous mirror would be is that you get diffraction effects from the edges of the segments.
Yeah, that will degrade the resolution.
Yeah, right.
I mean,
right.
back in the 60s, I saw the first segmented telescopes and was very negative, but apparently they're working out. But they still don't match the continuous surface.
Well, yes, but if you can't make the continuous surface,
Maybe 3 to 5
big,
microns, they come close.
Right, right. But yeah, so the shape of the point spread function that you get from the segmented mirror telescope is, you know, you'll be able to kind of recognize the pattern of the segments in there, basically. Yep. And then I think your question about the Earth observation images versus looking up is, it's about the geometry of the system, isn't it? If your source that you're imaging is at infinity, it's different geometry of the light entering the telescope than if you're imaging something on the ground.
Yeah, one more real quick comment was that Joseph Goodman back in the 60s used its Cernicki polynomials to analyze the atmospheric, and it turns out that the dominant Cernicki polynomial is a moving prism, shifting the image back and forth.
That's right. Yep, that's correct.
Does that agree with what you're finding?
Yeah.
Okay, we're getting towards 9:30, which is our usual cutoff time. from Maryland Space Grant Observatory, if you want to go across the street to look through the telescope, please come down. You're going to meet everybody over here. Next month, for December, we are having red dwarfs and brown dwarfs. And let us finish with one more big hand for Sarah Kendrew.